Right.
Hocam,
Hmm.
may I ask something about the problem we discussed earlier? So
Which one?
this one, on the board one.
Yeah.
So the integral is a line integral over. Eventually, I thought that it is a distance. I mean, dt refers to an infinitesimal distance over a path, but in the definition of Hamiltonian principle, you have referred to T1 and T2 as time, so I'm confused about it.
So, what? I don't understand. Could you elaborate? What's the confusion?
Okay, so is T1 and T2 referred to positions on XY plane or over
No.
the path? They are times.
No, there are two times. So the configuration path also has. It's not just the orbit; it also has the time embedded. So it describes the motion from one point in time to another point in time. And it gives this as, like R of t. That's your configuration path.
Okay, so we said that the integral on the board is a line integral, but
Yes.
we are taking the integral over time. So
Yes.
from my previous experience, like we were taking line integrals with infinitesimal distances, and so taking the integral over time just confuses me.
Yes, so the infinitesimal time interval corresponds to an infinitesimal part of the configuration path. So we are adding those paths.
Okay, so we are doing the same thing, but the
Yes.
representation is different.
Yes, exactly. So this thing is always going to turn into something times some length.
Okay.
Yeah.
Thank you, Hocam.
And it's going to become perhaps more clear when we write and we make the examples. Yeah. So is there any question about what does? So that there are two things to emphasize. First, the meaning of stationary, and either you get this or not. But I think if there's some confusion, again, some examples are going to help. The second thing is that there's this expression from time t1 to time t2. So this also includes the deviations from the path. So we have some paths, and you have some deviations from the path. So you have some unrealizable paths, but those also have to go from here to here. Okay? So we are fixing 2 points to endpoints of the path, and we are varying everything else. But the endpoints cannot change. So it has to go from some time t1 to some time t2. And again, this is important, and it's an assumption we are going to use. It's also physically important, not just mathematically. But again, if this is not clear, I hope the examples are going to help. Now, this is our Lagrangian. So, and that Lagrangian is in general going to be a function of our generalized coordinates. So I'm going to just rewrite Hamilton's principle by erasing all like this. And another thing that might be confusing is, why do we bother, right? So this is the other thing. I mean, like when you're learning calculus, you first learn differentiation, derivatives, and then you learn integration, because, well, derivatives are easier, right? So we already have something, derivatives. Why are we bothering with this? Well, that also is going to become clear when we come to the examples, that there are some things that's easier to handle using Hamilton's principle. But the basic idea is Hamilton's principle is something more unifying. It's something really simple. It's just one integral equation, and this kind of generalizes to other ideas, from optics to, I don't know, field theory, more easily. Okay, so I'm going to write my delta I as some delta of some integral from some t1 T2 or some Lagrangian. So I'm going to write this in terms of general coordinates. But and possibly equal to T of AT is equal to 0. Now, if our constraints are all polynomial, or if there are no constraints, it's the same thing, then Hamilton's principle is equivalent to Lagrange equations. Another way to say this is that Hamilton's principle is a necessary and sufficient condition for getting Lagrange equations and vice versa. Right? So that means that you can use Hamilton's principle to derive Lagrange equations, and you can use Lagrange equations to derive Hamilton's principle. So you just take Lagrange equations, substitute in there, do a little bit of manipulation, and you get that this is actually 0. Again, you're going to use chain rule again and again, but we're only going to derive Lagrange equations from Hamilton's principle, partly because Hamilton's principle is more basic, more fundamental. Now, an advantage of this formulation is that you can transform your generalized coordinates in any way you want, and the principle that you're relying on remains the same. Okay, so for example, it could be like using this one. And if you switch to generalized coordinates, this completely goes away. If you transform your generalized coordinates, right, for part of a problem, one set of coordinates is more convenient than the other, so you change them by a point transformation, whatever, and your equations are going to look completely different. Okay? Whereas Hamilton's principle looks always the same. Okay? It's always like this. Yes, when you plug the numbers in for different generalized coordinates, it's going to look different, but your fundamental principle is always going to look like this. So this is one advantage, and I think it's worth writing down. And this might look meaningless at this point. Again, some examples are going to justify this statement. So one advantage of this. This is important partly because this transforming your coordinates is something that's very, very powerful, right? It's in fact, bulk of classical mechanics. If you find the right transformation, then your problem becomes trivial. And unless you make that transformation and turn your problem into something trivial, you can't solve the problem at all. Right? As I said, yes.
Is this also relevant for the Lorentz transformation? Can we transform coordinates between different reference systems?
Yes, but so Lorentz transformation is a coordinate transformation. Right? So here I'm talking about like you're transforming the constraints there. Here I'm talking about like point transformations between different generalized coordinates. So you can express something in like Cartesian coordinates versus polar coordinates, something like that. Or in terms of the momentum, or in terms of the position in the Fourier space, they are both equivalent descriptions. To give a more complicated example, so those are still going to be your generalized coordinates and their time derivatives. The Lorentz transformations, you're changing the reference frame. So everything, if it's correct, is going to remain invariant under Lorentz transformations. But this is not an advantage that you gain because of this formulation. It's an advantage you gain because you took relativity into account and you express things in a Lorentz invariant way. Like, for example, Maxwell's equations are Lorentz invariant if equals ma is not. So it is possible that to write a Lagrangian formulation that is not Lorentz invariant. Did I get your question correct?
Yes, hocam. Okay, I understand.
The Lorentz transformation is something different. This formulation doesn't guarantee that. That's not what I'm talking about here. So, like, this is the point transformations. I think this is defined in the book. If it's not, I'm sure it's defined on Wikipedia or something. Okay, now let's get some examples. I'm going to look at all the examples from the book. The first one is the one-day problem, and they're asking you to find that the shortest, well, describe that one. Let's read what the example is. So these are all classics, and I want to go over these. Yeah. So we start with a one-dimensional form, and then we are going to generalize this to a multi-dimensional form. Now, yeah, there's a point I want to make here. Let me again erase it. So how would my path look like in one dimension? Okay. So obviously, we don't have interesting one-dimensional problems encounter, but we start with this because the algebra is simple. What does the configuration path look like? So the example they give there is this, and then we're going to define y prime as the derivative with respect to x. So y is our dependent variable, x is our independent variable, and we're gonna go like this, and you can draw a path like that. Is this our configuration path? Is this the path that we're going to be dealing with? What is the analog of this for the stuff that we previously used? So I did check perusal this time, but there were no comments this week. So nobody wrote anything. And there is a lot of room for confusion. The book has a lot of typos, for example. Nobody commented on those. It's very annoying.
Hocam, there might be a problem with the perusal assignment. I mean, I added comments yesterday night and I couldn't see anyone else's comments either. And that struck me as...
I checked yesterday evening. There was no one. So it's not you, it's the other people.
Okay. Yeah, I thought I couldn't see other people's comments because of some configuration.
I couldn't see it either, and I can't imagine the configuration problem that leads to that. But it's possible. I'm not saying it didn't happen. But what will be the analog of this for what we have done so far? This is important. This is something peculiar to one dimension.
So could it be the shortest distance between 2 points?
Well, we could do that, but the shortest distance between 2 points is what?
A line?
In Euclidean space, it's a straight line, yeah?
Yeah.
But what's it in one dimensions? In one dimension, everything is a straight line, right? So your configuration path would in fact look like this. So I'm going to put it like this. So this is my y-axis. I start at some, x1, you go to some x2, and your configuration chart you would do like this. So this is parameterized by x, right? So here, x is playing the role of time that we before. Time was our independent variable, and our coordinates, the Cartesian coordinates or the generalized coordinates, whatever, was our dependent variables. Now here we have one dependent variable, one independent variable. So x is playing the role of time, and this is something you're going to see, especially in math books. So this is not, I don't think the book is trying to be hard, try to trick you, try to confuse you. This is something you will see, so it's best that you see it here. So the configuration path that we have been drawing so far will look like this in one dimension. And you have one, in the configuration path, when we are drawing the configuration path, we use the dependent variables. And in the path, there is a parameter, our independent variable time. So you draw, when you draw it this way, well, this also shows the configuration path, of course, but this is not that now there is no parameter of the path or anything like that. This is not how we use the configuration path. But you could choose, denote different parameterization of this path by using different paths. Okay? So these will all be the same. Yeah. There is, of course, if this is really the analog of time, the x coordinate as you're drawing the path should be monotonous, increasing, and so on and so forth, but I'm not going to delve into those issues. Now, if our correct path is y of x, we can introduce deviations by some parameter alpha. Okay? So I'm going to include this alpha, and that is going to be, our dependent variable x plus the alpha. So this is going to be, all the paths that I can draw, and this is going to be the correct path plus alpha times some arbitrary function. Okay. Now, I'm saying this is arbitrary, but it has to be differentiable at least twice. It doesn't have to be analytic or anything like that. It has to be differentiable at least twice. And vanishes at endpoints. Okay. So that our paths always match. Now imagine that this is our correct path, that this is our original y of x, and this is something like y of x plus, I don't know, 0.18 of x, some function, right? Some small number and some function. So this, you can always do this. You can always parameterize these deviations, and instead of y of x, we're just going to write that this alpha parameter is 0. But this is completely equivalent to saying this is y of x. This is our original correct realizable path. Okay. Now we are going to write this. I think I would erase one of these. Principal, our integral, and make the deviation. The advantage of writing it this way is that it allows us to apply chain rule and things like that. So our integral j is now going to be a function of this parameter alpha, and we're going to have it from x1 to x2, some function of y of x and alpha, y prime of x and alpha, and x. Okay, dx. Now, as you see, x has replaced the role of t because it's now our independent variable. Okay. Now, our requirement is that j by the alpha. So this is the duration of j with respect to alpha. When that deviation is 0, this has to be 0. So this is the condition of stationary. Now, the reason why we did this, we express this way, is that because we know how to do this. Okay? So if we can express our stationary value with this simple derivative, then I can actually take the derivative of this and apply chain rule to this function, because I can move the derivative inside the integral sign, so differentiate under the integral sign, and get some expression. Okay? So there is in fact some logic to this. It's not something coming to me from an oracle. There's a very good motivation in writing it this way. Unless you parameterize it this way, then it's not really clear what this means. Okay? What does it mean? And the correct path. You can't even define what the correct path is in terms of your parameters. So to be able to write this expression, Hamilton's principle, in some mathematical form, we first parameterize our function and then express our stationary value condition or the Hamilton's principle using this way. Any questions? Again, I'm not really sure how much you know these. If I'm just being too elaborate, you can always let me know, and I'm happy to skip over it. Now, let's erase this one as well. And here we are just going to apply chain rule, ej by the alpha. As I said, I'll just move the differentiation under the integral signs. You can always do. So this is del f by del y by alpha plus del f by del y prime by del alpha times dx. Okay. Now look at the second part. Get this part of the integral. That we can write that this is a derivative of y with respect to x. So it's in fact this little thing here is in fact the second derivative of y. So this is del f del y prime del square y by del x del alpha. Okay. And now I'm going to take this integral. So I'm just looking at the second part. x1, x2, del f by del y prime, del square y by del x del alpha dx, and I'll integrate by parts. Do you remember integration by parts? Is there anyone who doesn't remember integration by parts? I'll show it anyway. So I won't feel bad when I ask about this in the exam. By the way, do not think that you can look these things up and so on and so forth. Okay? You are required to remember something as fundamental as integration by parts. So this is the basic idea. It's basically saying that you can take this, differentiate, integrate, and you get this. Right? How does it apply over here? I'm going to call this u, and I'm going to call this one dv. Okay. Same notation. So this is this integral. It's now going to turn into u times v. So it's, let's perhaps explain this more carefully. Del square y by del x del alpha dx. Then your v is going to be del y by del alpha. Okay. And I can write this. That integral. Oh, just in over here as del f by del y prime, del y by del alpha from x1 to x2 minus. So this is the UV part. That UV, of course, you need to integrate. You need to put the values at the endpoints. If it's a different integral, if it's an indifferent integral, you don't keep it. Minus integral from x1 to x2 e by dx del f by del y prime del y by x dx. And here, sorry, this is not here. This whole thing is the and this again g. Okay. So you all right. Any disagreements? Any questions on where these things come from? Anybody feeling like I'm cheating because I'm looking at my notes? I wrote those notes myself. I didn't actually copy them from anywhere, but I'm sure this is available much more cleanly in a number of places. Any book on calculus of relations should cover this. It's probably in total environment. Just skipping here. All right, now this term vanishes. Why?
At the endpoint, because we selected alpha to be 0, the deviation.
Alpha is not 0 at the endpoint. Alpha is not a function of time. Alpha is not, in this case, alpha is not a function of x. It's just a small parameter. It's not a function of anything. But you're on the right track. You're definitely on the right track. It has something to do with the property of this deviation at the endpoints.
Hocam,
What
we
does
set
vanish at the
the
endpoint?
we set the eta is 0 at endpoints
vanishes
and
at
starting
endpoints,
point.
right?
So
And the
the
partial
change of
derivative
the
of this with respect to alpha is just eta. Right. So sometimes, especially in electromagnetism, these terms drop out because they cancel. Okay? They have the same value at the surface. So these are called the surface terms. But here, it vanishes because it vanishes at both points. Okay? There is no cancellation here. You're not actually subtracting out the surface terms. The surface terms are both 0. This is something, I don't know. You also see this in EMT, but in EMT, I think the other case is more common. At least that's what I remember. So this one goes away. This is 0 because this is 0. And then you're left with this. Is the negative sign correct? I think this is correct. So then dj by d alpha, if you go back, remember that this said the two parts in the integral, but this is just the second one, can be now written as from x1 to x2 del f by del y minus d by dx del f by del y prime. This is bad notation, but bear with me. Del y by del alpha dx. Okay. And we want this, at the correct path. Correct path is alpha equals 0. to be 0. But this is just theta of x. Now, I already talked about this trick in the discrete case. This is just the extension of the trick into the continuous case. So for a sum, I was saying that there are these terms here, and there's an arbitrary multiplied by some arbitrary function. And if this term is identical to 0, because this function is arbitrary, all the individual terms in the sum has to be 0. We can extend this idea into the integral as well. So this is an arbitrary function. There's nothing special about it. I mean, it's arbitrary except for the endpoints. Okay? But the only way that this integral is going to be 0 is if this part of this integral, this equation, is equal to 0. This expression is equal to 0 identically. Why? Just imagine it's not. Then I can choose this function in such a way that it's 0 everywhere and non-zero at the point where this is not 0. Then the integral is going to be non-zero. Okay? So because this is arbitrary, from the condition that this has to be 0, follows that our y minus d by x by del y prime is equal to 0. And this is, of course, the one-dimensional Euler-Lagrange equation.
Hocam,
Yes.
where did the first term come from when we wrote the
So this originally, this derivation had two terms, right? So this is the manipulation of the second term. This thing here, this star over there. I erased it. I'm sorry. I just don't have the space. This star was in fact the second term, and the first term was this times this. If you go back, so we made a variation. There were two terms in the variation. The variation with respect to
del y.
So with respect to
over
y
del
and then the y prime. So this is the variation with respect to y. The manipulation of the term with respect to y prime gave us this term.
Okay,
This times that. Yeah?
Put it in parentheses.
And then I took this into common parentheses.
Thank you.
So I'm sorry, it's just if this was a full classroom, I could point this out, but you need to look at your notes. Or if you're not taking notes, I don't know how to help really. I can speak, but it's not going to be.
Yeah, I checked my notes. Yeah.
Okay, excellent. All right. So this is the Euler-Lagrange equation for one dimension, and obviously this is it's very, very similar to what our Lagrange equations look like. Now let's look at some examples for this one-dimensional case. The first one is, something that everybody talks about: the shortest distance between 2 points in a plane. Yeah, so I'll keep this. So before I erase, are there any questions or any objections on what's going on? Okay. Now, I'd like to reemphasize that it's not enough that you can follow what I'm doing. You need to be able to do this yourself. I really did do this myself before coming to class. Okay, if you don't do this yourself, when you try to apply these to problems, you're going to fail completely. It's not enough that you understand what I'm doing. You need to be able to, do this integration by parts and all the steps by yourself in some way. Just go back, and if you fail, look at your notes, and if you can't figure it out, ask me. Okay? And there's a reason why I'm taking the time to do this, report all these steps. I do think it's very useful, and you are going to need it. So, example 1. The shortest path between points in plane. Okay. So we want to have our integral something like this. Okay. Now here, I'm trying to confuse you a little bit. It's deliberate, so I'm hoping I'll get some questions. So what's this ds? So ds is generally defined like this: square plus square half. Okay, the square root of the x squared plus dy squared. Sometimes you see ds squared is equal to x squared. So this is the general notation. When I write it this way, it means the square of the x, not the d of x squared. Right? I'm not going to put parentheses around dx over here. It's the general convention. You should nobody puts parentheses there, but you should learn this combination. Okay, so we're gonna look at this, and this is going to be square root of dx squared plus dy squared. Or I can manipulate this plus dy by dx squared dx. Okay. And I got 1 plus y prime squared dx. So this is the length, and I want to look at the shortest path. What kind of path is going to be the shortest length for this? And of course, for that, I need to take the variation of this and set it to 0. And I know how to do it. I'll do it this way. Okay. So this is exactly like the function that we did before. My f of, which is in general a function of y prime, and x. In this case, is only a function of y prime. So I can calculate these partial derivatives. One of them is trivial. The partial of this f with respect to y is 0. The partial of this f with respect to y prime is 1 plus y prime squared to a half minus a half, is it? No, sorry, a half. That's so. Yeah. So there's a half coming from the exponent, and there's a 2 coming from the exponent of y prime. So they cancel. I end up with a prime. If I take these and substitute in here, what do you get? Well, you get the d by dx of this expression, y prime, 1 plus y prime square root is 0. What does this mean? The derivative of something is 0.
It is a constant.
It's a constant. Right? This thing must be a constant. Let's go C. So y prime over 1 plus y prime 1 over 2 is a constant. Now, if this is a constant, the only way this is a constant is if y prime itself is a constant. Right? This is a function of y prime. And it's not a constant function. It kind of depends on y prime. The only way that this will be a constant, it doesn't depend on x or independent variable, is if y prime, in fact, is a constant.
Hocam, so
Yes.
y prime being a constant is very intuitive, but can we be 100% sure for any given arbitrary function we have in such a problem? Or
Well,
is there an algorithm
just
to
take
make
this
Mhm.
and solve it for y prime. Like move it to the other side, square both sides. It's a quadratic. You'll just solve it for y prime. You're going to find it's just some constant. It's the constant plus some algebraic manipulation.
like solving a differential equation with
No, it's an
regular-
algebraic equation. It's not a differential equation. So just take this and solve it for y prime.
Mhm.
I call it C.
Mhm.
Let's do it. let's do it.
Okay, I understand. Like y prime being just a variable.
Yes.
Okay.
Yes. So in this case, there is going to be a solution.
Mhm.
Okay. The only complication I can imagine is that you write this, there is no solution. Right? If this function was something else, it is possible it doesn't have a solution, or there's complex solution, something like that. Okay?
But
That will be a complication. Yeah.
sorry, cannot be a case that y prime is being a function of x also.
No, it can't.
Okay.
How can it be? I'm showing this. Let's show this explicitly. So this is some function of, no, we can call this y prime, we can call this anything, it's a constant. Yeah. Now I'm going to have g of y prime being defined as f of y prime minus d. This is 0. Yeah. Now I can solve this. So it is possible that because of the property of this function, that there is no solution. But if there is a solution, it's going to be a constant solution. It's just going to depend on what this function is and what this value of c is. I'm going to find the roots of this function. Yeah. This function g of y prime, whatever it is. If this is defined, if you have an expression for it like we have here, then you can write an expression for g of y as well. Yes?
Yes.
Okay. Then that function is going to have roots. Now, if it's an observed function, it's not going to have roots. But in this case, it is going to have. And those roots are the value of your y prime. Those roots are just numbers. Well, not exactly numbers, they'll depend on c, but they won't depend on x. Okay, so roots of g will give values of y prime. And they can't, there's just no way they can depend on x. There is no x here. If you can find some values, they cannot depend on x. It is possible you can't, because the function is unphysical or has some very peculiar properties. I can't imagine what. But if you find values, they cannot depend on x. They have to be constants. There is no x here. Where is the x going to come in? Does that convince you, or?
Okay, Hocam. I understand your point in this discussion. Thank you.
Okay. All right, but if y prime is constant, remember what y prime is. It's constant. I can really integrate this. That's probably. That's the general solution, right? If y prime is a constant, then y must be a linear function. It's constant is bn. You take this, you take the derivative with respect to, m. Take derivative with respect to x, you just end up with m. So p is another integration constant. This m is a constant that depends on our first integration constant. So they are kind of determined by the endpoints. So given your 2 points in plane, they are going to determine your slope and intercept. But it has to be a straight line. So by setting this del j equal to 0, we find an extremum. In this case, it happens to be a minimum. In the plane, a straight line is the shortest distance. This doesn't guarantee that you will in fact find the shortest path, but in this case, we end up in the shortest path. Yeah, go ahead.
may I ask, it's going to be a simple question, but I think it is also fundamental. Here, considering the physical quantity of the equation, the action we defined at the beginning of the class lecture, it was in joules second. The action was in, Lagrangian is in joules and dt is seconds, so it was in joules and joules seconds, and now we are doing something in meters. If we consider length between 2 points, I have done some reading about action, and I have found 3 different action definitions: the shortest path, the lowest energy, let's say, and the lowest time or minimum time consuming paths. So there are 3 types of equations that can be defined for action. I might be wrong, but that was something that I understood from what I read. Can you elaborate and make it more more clear for me?
So the reason why we start in abstract and use x instead of t is that because we are familiar with this, right? So we have a function y that depends on x. So this is completely general. This doesn't have units or anything like that's attached to them. And by saying that that this function that when we draw a path between 2 points, and the endpoints are fixed, and we're looking for a stationary value of this integral, requires that that function satisfy this equation. This is just a one-dimensional function. Or the path. I'm sorry, the path is satisfying this equation. Now, this is just a Lagrange equation. It's not action. It's not anything. When for your function f, well, we are going to do a multidimensional generalization in a second, or in an hour. I don't know. And then when you substitute your Lagrangian for this function in the multidimensional generalization, you're going to get your actual action. That's what the Hamilton's principle is about. But at this point, we're completely abstract. We don't have any units or anything like that. Now, it is possible to express a variational principle in more than one way. Okay? So, for example, one way to define a circle is to say that it's the curve with the largest area enclosed among all the curves with fixed length, among all simple closed curves with fixed length. Right. So that's the definition of circle. It's perfectly same as saying that the geometric loci of the points equidistant from a given point in the plane. It gives the same answer. Now, so different definitions of action will be useful for different situations. As I said, this variational principle and Hamilton's principle extends to optics, for example, where there are no forces, there are no energies, like you can't push, photons or anything like that. They don't accelerate. But the paths that the light rays take can be expressed in variational principle. And likewise in field theory. In field theory, I think the dimensions are closer to what you have in classical mechanics, but the physical meaning of things, no, actually dimensions can be completely off as well. But you write some Lagrangians, and the dimensions of Lagrangians can be something different than the joule seconds. Sorry, joules. So maybe you're referring to those, I don't know, but it is possible to have a variational principle to describe a problem, and the function you're interested in doesn't have dimensions of energy. It's something completely different. Like in the case of circle, what you're maximizing is area. So perhaps it's path times path. I don't know. Maybe that dx times dy, something like this, or it could be something from optics. I don't know what you use in optics, but I know this variational principle does work in optics. So again, if you tell me what the specific action is, then we can discuss it. But it could be just overextending the use of the term action. For us, action is going to mean just one thing: Lagrangian and this integral from some T1 to T2, but people can be using it for other purposes.
Nice. So while reading the chapter, I wanted to learn more about the definition of action, and then I found that it was first used in optics for light. I think the path
For
the light
using
takes.
Fermat's principle.
Exactly. So I tried to evaluate that using action, and I derived the diffraction and so on. But the problem was, when it is the short, for example, probably we're going to come to Brockus-Takram problem, the shortest time consuming path. So with different problems, the integral we take for action changes. For example, if we are searching for the extremum points for the time, the action is defined as integral dt, just time, and then we divide it by s dv and so on.
So I see what you mean. So you're saying y prime. So you want to call this action, right? So this is something completely arbitrary. This f is not defined. It's just some path, and it gives some this y is a function of x. So this is what you want to do, right? Do you want to call this one action? Now it's not wrong.
Yes, exactly.
You can. So for Brockus-Takram problem, we are going to call, we're going to end up with a function like this, and we're going to call, well, we're not going to call it action, but you can. And we are going to be applying the principle of least action. But the principle of least action, strictly speaking, in our case, at least for classical mechanics, applies to the case where this is in fact Lagrangian, and this is time. And that we are going to call action. From that principle of least action, you get Lagrange's equation of motion. From this action, you get the Euler-Lagrange equations. Euler-Lagrange equations are more general. And so they apply to anything, optics, field theory, whatever, geometry, this, that. The Lagrange equations of motion, as that equation of motion part indicates, corresponds to mechanics. And in mechanics, the Lagrange equation of motion is derived from the action of where this is the Lagrangian and where these are time, and the coordinates has certain properties and so on and so forth. But just feel free to use action more generally. That's fine. But then you are referring to Euler-Lagrange equations or the multidimensional generalization of this. And you're not really referring to Lagrange equation of motion. And for the Brockus-Takram problem, we are not going to be solving Lagrange equation of motion. We are going to be using Euler-Lagrange equations. And even though that sort of corresponds to motion, it's not going to be, because we are not trying. We are going to be looking at this like dt, and we're going to manipulate that dt. So it's going to look like this: some function times independent variable by using energy consideration and so on and so forth, and use Euler-Lagrange equations to get the condition for that integral, the total travel time, to be minimal. Can you call it action? Sure, of course you can call it action, but it's not the action in the Hamilton's principle of least action.